I turn this to curved, notice that engine gets power. When it goes to straight, no power. When it goes to curved, it gets power. Straight, no power. So what?
Hello, I'm James Ingram. This video was digitized from a 1992 videotape series named V9202.
Let's take a look briefly at some of these components that we'll be talking about during this text. You commonly hear people throwing the names around. You hear people talking about a 1015U single isolating track. That's basically this item over here. One of the rails, in this case the rail closest to the camera, is gapped. So you can use this thing, actually two of these, to form a block. And they have little terminals in the center. You can wire to different rails. For instance, you can wire two of these terminals will wire to this rail, and two of these terminals will wire to this rail, and then the other terminals would wire to this rail. We don't need to use that rail for our purposes. We talk about a 1201 switch motor. That's this item here. Basically, most commonly found on a switch. Mounts on the edge of the switch, and this arm here throws the parts of the rail that comprise the moving points part of the switch. 1203 points is essentially a set of double pole, double throw relay points. These things snap into the end of the 1201 motor so that your switch motor can drive both a switch and these points, which will open and close circuits. Or in the way I use them, I just use a motor by itself usually to drive these points, so the motor is less heavily loaded. I'll see if I can demonstrate. These points pop into the end of these motors. I'm going to see if I can demonstrate that once real quick. Basically, there's a cover plate on the end of the motor. There, I've got it. The cover plate on the end of the motor that pops out. Then you've got a hole and you can pop the points in. Let's see if we can demonstrate that real quick. You can see I popped out the cover plate, which is laying down there in the paper. And now this motor is open on the end, so we can pop these points in. Since the arm is going that way, away from where I'm pointing, I want to make sure these two contacts, which are movable, are pointing the same way, so they'll mesh with the insides. You can see how that snapped in there. Now we've got a 1201 motor driving a 1203 point. So when this switch motor is actuated, these points are opening and closing circuits here. We can use that. Basically, this is what we use to power the, not to power, but to control the block section of track on the automatic block systems. When it's mounted on a switch, this same unit typically looks like that. You can see I've got the motor oriented the same way. There's the motor mounted on a switch. In this case, this switch motor is also driving a point. Let's pull it in a little closer here. You can see this motor is oriented the same way as this motor, and it's driving a switch. This item here is a 1700 track contact. Basically, when an engine with a magnet passes over it, it makes a momentary contact inside. It's basically a normally open type of switch. But when an engine goes over it, it makes a momentary contact that momentarily closes a circuit, which typically used to actuate one of these switch motors to cause something to happen, either a switch to throw, or just a pair of electrical points to shift. And that track contact is typically actuated by these 1701 magnets. These mount on the bottom of the engines. They snap on the bottom of most of the LGB engines. Here's a LGB engines. Here's a LGB engine. You can see the magnet is on the bottom of it. I'm going to unsnap it and snap it back on just to demonstrate. So that's how the magnets unsnap and snap on to most of the LGB engines. A fairly simple process. Thus, when that engine with the magnet passes over that track contact, let's put the track contact in a piece of track. There, it snaps in. Track contact just snaps in a piece of LGB tracked, basically like that. So when an engine with a magnet on the bottom of it passes over that track contact, it makes a momentary contact, which is sufficient time to throw a switch motor. For units that won't accommodate a magnet by snapping it on, a few of the LGB units or some other non-LGB brands, often a magnet can be taped on the bottom. The instance is this hand car. This is an LGB hand car, but apparently they had no intention of having a magnet put on it. I put the magnet on for some of my later demonstrations, but you can see the magnet extending from here to here. That magnet, I just duct taped it on the bottom. So you can usually duct tape the magnet on the bottom of most engines, even if the magnet doesn't readily snap on. It's not quite as convenient, but it will work. The other item we talk about commonly is the 5094 block signal. As you get it, it comes in a big red package, which looks essentially like this. You can see the, if I can get it in the camera, you can see the number. There's a 5094 block signal, and its accompanying red package. And let's take that out and look at it. Comes with some diodes and stuff which you don't normally need. Instructions. Main thing is it includes two 1015Us. These are the same unit as this unit here I was working with earlier. The only difference is I've removed the top. They come with a plastic cover, which most people usually keep on. I usually take them off because I'm always attaching a wire to this terminal strip. But this 1015U I've got in my hand is identical to the unit in the box, except that the unit in the box has a plastic cover on it. But anyways, the 5094 package, which is shown in the white box here, includes two 1015Us, the 5094 motor, plus the 5094 dual semaphore signal arm. This arm basically attaches to the top of the motor. You just push it down. You have to line up the I've got it backwards. You have to line up the let's see if it shows up in the camera. You have to line up the groove down here. You have to line up that little slot with the nub on the top of the motor. Can't seem to get the lighting optimized here, but I think you can get a sense of how that semaphore arm snaps on top of the motor. That's better. So here's what our 5095 motor looks like, and make a mental note that that 5095 motor looks an awful lot like a switch motor. I think I can use a light again. That 5094 motor looks a lot like a switch motor. In fact, that usually when it comes out of the box, it has the points. I've removed the points from this one. Typically, it has these points in it. When you take it out of the box, it'll usually have that point in it. And the first thing I do is unsnap the points, like I did earlier with this unit, pull them out of this motor, and move them over to the switch motor, and snap them in a switch motor. Then I use this thing to do the electrical driving for the block signal. I just let this thing without the 1203 points, just by itself. I let it drive the semaphore arm. Therefore, this motor just drives the semaphore arm. This second switch motor, which I add, now drives the 1203 points, which were originally, as shown now, which were originally snapped into this 5094 motor. We're referring a lot to Radio Shack speaker wire for making AC connections to power these blocks. I may as well take a quick minute and show those while I'm thinking about it. What you see in front of you is the AC side of one of my transformer units. Basically, AC power goes out of the transformer via these wires. I've actually got three plugs here. Only one of them is connected at the moment. But you have male ends and female ends. I think both these units are male ends. In that case, you can use a coupler like shown here in my hand, which gives you two female ends to couple two male ends. So with these couplers, you can use any combination, these Radio Shack wires. I think they call these RCA plugs. And it's basically your standard garden variety connector you use to plug like a stereo speaker to a stereo receiver. So you can get them in all lengths and sizes and colors at Radio Shack and other electronic parts supply stores. But it's a convenient way for me of just making my AC connections real quick, because I don't have to mess around with the screwdrivers. I just connect things with these. Let's take a look at the DC connections while we're over here. This is the DC side of the transformer. What I use for these connectors are, I believe, a standard connector for slot for electric racing cars. Like, what am I trying to say? Radio-controlled cars. And I get these at a radio-controlled car parts supply. They're made by Tamiya, but it's basically a connector I use for DC. And again, it's another type of connector. It just snaps in and snaps out. You can see I've got two of them coming off here. I can run to two different places in the track. So again, I can hook up my track contacts. I can hook up my DC track power just by using these things without having a screwdriver, which makes it more convenient. I can almost do it by one hand, and not quite, apparently. And since these DC connectors from Tamiya that I use are incompatible with my AC connectors over here from Radio Shack, I can't accidentally get my AC and my DC mixed up. So it's nice to have the AC and DC be two different kind of quick connectors, so you can't mix them up accidentally. Looking at this 1700 track contact again, let's consider a simple schematic circuit as shown on this paper. Down here at the bottom is an AC transformer. Up on the top here is a light bulb. Over here is shown a 1700 track contact. Again, this is a normally open switch. It's shown open now. When you put the magnet near enough to it, this switch will close and complete the circuit. I guess the nearest thing I can think of this thing to this switch off the top of my head is like a doorbell. When you push on a doorbell button, that's a normally open switch, and it makes a momentary contact while you press on it with your finger. As soon as you let go of a doorbell button with your finger, the switch opens and the doorbell stops ringing. This is kind of similar to a doorbell button in that it wants to stay open and it won't stay closed unless you hold the magnet next to it. In this case, instead of pushing on a button with your finger like you do with a doorbell button to close the circuit, here you hold the magnet next to it to close the circuit. But they both have the same normally open characteristics, in the sense that when you take the magnet away, or as with the doorbell button, you take your finger away, they go back to normally open if left on their own. So on their own, they won't complete a circuit. You have to cause them to complete a circuit. Here you hold a magnet next to this thing. So you can see at the circuit as shown with this thing open, this light bulb won't light because this has a path for electricity, but there's no path the other direction. Now, when a magnet is held next to this 1700 track contact for this circuit, and this circuit is closed, then you would have a closed circuit. Since there's a diode in this circuit pointing to the right here, and it is a AC power, you'll get what they call halfway rectification. You'll get a current flowing in the direction of the diode. it'll take essentially the AC, which is trying to go both directions, and the diode will let it go one direction but not the other direction. If you want a really crude analogy of how this diode works on an AC current, which will probably offend you if you're any kind of electrical person, but a real crude analogy is kind of like when you're jacking up a car with an auto jack. You push the jack up and down with your hand in both directions, but the jack essentially either raises a car or lowers a car depending on the way it's set, but only goes one direction. This diode works kind of the same way with AC current. The AC currents, AC voltage is trying to go both directions, but this diode only lets it go one direction. So like a car only goes up on the jack or down on the jack when you're pushing both ways with your arms on the handle. Likewise, this thing just lets current flow one direction. In this case, the current would go out this way, assuming the current goes the direction the diode's pointing. That's the assumption I'm making. The current would go out this way through the light, come back here through the diode in the direction it's allowed to, across the closed switch that we're assuming is closed because a magnet's being held there, and back to the AC transformer, completing a complete path. Let's take a look at that actual circuit. Here's our transformer. A little closer. Here's the red wire going from the transformer to the light. That's essentially this red wire coming out of the transformer here and going out to this light. The blue wire going out to the track contact is this one right here. That's this wire here. The other wire, the green wire, shown going from the track contact. That green wire there, shown going from the track contact out to the light, is this green wire here that goes out the track contact and over to the light. So this is normally open circuit, so there's no circuit being completed. Again, like your doorbell circuit, nothing happens in the front of your house at a doorbell circuit if nothing's going on. Now, if this was a doorbell button and you pushed on it, your doorbell would ring. In this case, if we activate this by using the magnet, we can close that contact and make the light light. Let's try that. You can see as I bring this magnet down next to the track contact, it closes a switch inside and makes that light light. And think of this being kind of analogous to making the doorbell ring. If you walk up to your doorbell and push on that button to close the doorbell circuit, you complete the circuit and your doorbell rings. In this case, the light going on is analogous to the doorbell ringing. So you can see that's a momentary contact. It only is closed for a small period of time when the magnet goes over it. Now, when an engine with the magnet, here's that same magnet on the bottom of this engine. I'm just going to slide that engine across the track contact, but notice when the engine gets over the track contact, you'll see that you should see the light go on briefly. You see out there, I think you can pick up on the camera how the engine makes that light light up. Now, normally, you don't use this track contact to activate lights. I'm just doing this to attempt to show how it works. Normally, this track contact is wired to a switch motor, and you activate a switch motor. Even if you want to turn on lights in a station or something like that, you wire the track contact to the switch motor, which then throws those 1203 points, which stay closed once they're thrown. That'll keep the lights in the station on until you turn them off again via another track contact. You only get a split second of contact here, as you can see. If I push that engine across there more like a normal operating speed, it's just on for a part of a second, but the motors throw pretty fast. And according to LGB, you can drive up to 2 switch motors with one of these track contacts. This is a 28-volt bulb, which is why it glows fairly dimly. I didn't want to put a low voltage bulb in, which might glow more brightly because I'd be afraid of burning this track contact out. This is not a high current device. So I put a high resistance bulb in that hopefully was going to draw just a small trickle of current and not damage this track contact, and so far it seems okay. I have burned them out. They can be burned out if you wire them up and get too high of a current going across them. Now this, as I mentioned, the halfway rectification, this track contact gives a direction to this current. In this case, it doesn't matter with the light bulb because a light bulb doesn't care what direction the current is going, but depending on how you wire this thing, it'll throw the switch motor different directions. I generally consider the center. Let's go back to let's look at it here if we can. This thing has three, I think you can see the tops of the screws shining. It says three connections. I consider the center one the input, then I come out of either one of the outside ones as my output. In this case, I'm coming out of as I'm looking at it, let's turn it. Now as you're looking at it, this wire is coming out of the right. You can come either out of the right side or the left side. If you come out of the other side, the current will go in the other direction. So you control which side of this you come out to control which side you throw the switch motor to, assuming you had a switch motor wired up here instead of a light bulb. If we go back to our diagram we were looking at a minute ago, we first started out with the AC transformer here, the 1700 track contact here, and a light bulb up here. We can now replace that with another diagram showing in place of the light a honest-to-God 1201 switch motor, which would be this diagram here. Again, here's AC power down at the bottom, AC transformer, the 1700 track contact. I've got that mislabeled. That should be 1700 rather than 1701. Let's make a quick fix here. It's not fixed. In a 1201 switch motor up at the top. This is really this is shown schematically down here, but this wire here is actually goes in the center of this 1701 track contact. Remember I said consider the center terminal your input, so on the actual track contact this wire will go into the center, and this one will come out the left side as you look at it. Now in that getting started booklet I showed you a rough draft. One of the parts of that is this little diagram, which I know doesn't make any sense the way it's just scribbled up there, but basically it gives me the four combinations of ways you can wire. Basically you got two wires going from your transformer to your switch motor, and one of those wires goes through the 1700, and given that there's basically four variations of the ways you can run those wires, and by trial and error, I guess I should say by observing what happens, I can document which way the motor's going to throw depending on how I wire this thing. So using that I can make this sketch to say that when it's wired like this and the 1701 track contact is closed, it'll cause the arm of the switch motor to go to the left as shown by the arrow there. If we wanted the arm of the switch motor to go the other way, we would use the other diode that we had earlier with the light bulb, the diode that is shown coming in, because that would cause the current to go the other direction. It would pull the arm the other direction. But this combination of wiring will cause the arm to go to the left as the arrow is shown pointing there. Now let's look at that in the actual hardware. The red wire that's shown going from the transformer directly out to the right terminal of the switch motor is this wire here. This red wire here goes from the transformer out to the right terminal of the switch motor. And this other wire coming out from the transformer to the center of the 1701 track contact, the blue wire, that's this wire right here that goes into the center of the 1701 track contact. This blue one here goes into the center. And again, consider that the input wire going into the center of the thing. Finally, the green wire that comes out, one of the output wires of the 1701 track contact, this green wire goes up to the left motor, the left terminal of the 1201 switch motor. Let's look at that wire. Here is the green wire coming out the left side of the 1700 track contact and going up to the left terminal of the switch motor. And what I'm claiming is when the magnet is actuated, the arm will go to the left, which will throw the switch from straight to curved. You can see it's in the straight position right now, and you can see what happens. It goes to the curve. Now once it gets to the curve, nothing happens because this thing is always pushing current one way, so It's just trying to push it to curved when I close the circuit by putting the magnet down there, and it's already in curve, so it goes nowhere. But if we push it back manually to straight, it'll push it to curved. Now you can see this is this could be the basic for what I'll demonstrate later on in the tape as an automatic route selection film when an engine goes through a switch and throws a switch behind it. Let's say an engine was traveling, coming this way with a magnet on it, and we go across the straight switch. Now it would go across that track contact, and you can see it would throw the switch to curved. Now if that was a loop of track, and that engine traveled around the loop and came around again, the next time it came to the switch it would go curved. So this could be a simple basis for a simple automatic route selection system where you cause a single train on a track to travel two different routes. Let's look at that with an engine. If I put this engine on the track, and it still has a magnet on the bottom of it, and just manually pull this engine through here, let's see what we can see here. Notice the switch is straight. I think the camera picks that up. Now as this goes over the magnet, see how that engine throws that switch to curved. Now if that engine traveled around the loop of track, let's say this is the return loop to get up here again, and it comes around the loop and encounters a switch again, which is now curved, you can see what's going to happen. It's going to go down the curved path. Let's assume we wire one of these things up now to the other side. Pretend we leave this one still here, but we just make another simple circuit like this and put it on the other side. Now we've got that track contact on the other side. It's still going to do the same thing as it did before because it's still wired the same way. It's going to throw the switch from straight to curved just like it did before. However, to have it operating over here, we want it to do the other thing. We want it to throw it from curved to straight. So we can change the output part of this 1700 wiring around just by moving this green wire from one side to the other side. Let's do that. Remember, the center wire is the input wire, so we're going to leave that there. We're just going to move this green wire from one of the outside terminals to the other outside. Basically what we're doing is routing the power, or I should say the current path through the diode that's going the other direction, so it'll halfway rectify current in the opposite direction, which will make the current flow the other way. What I did by reversing those wires is kind of again, to use my sloppy analogy, is kind of equivalent to when you're jacking up an automobile, pushing that little lever on the jack that changes the direction. So you keep moving your hand and arm the same way on the handle, but now the automobile travels the other direction. If it was going up, it'll turn around and start going down. Likewise, this will do the same thing with the AC current. It'll force the AC current to go in the other direction, which will throw our switch motor in the other direction. Now we should go from curved to straight, and you can see that's what happens. This magnet now, when it activates a track contact, causes it to go from curved to straight. So you can see now if an engine was coming through this way, and encountering the curve switch, we get down this track and would throw that switch to straight behind it. So the next time it came along, it would go straight. Let's look at that with the engine. I'll just again pull this engine through here. Let's pull this thing up a little bit. And you can see when the engine goes over the magnet, it flips the switch to straight. So this if we wired this track contact up here like it is now, and wired the one that was here a minute ago up the same way, in other words, had two of them here with the wiring superimposed, so to speak, be a total of about 5 or 6 wires. You could have a simple automatic route selection that would the train would go through the switch one way and throw it to the opposite direction. The next time it would come along, encounter the curve switch and go through here and throw it back to straight. And next time it would come along, go through the straight switch, the track contact here would throw it to curved. And when it came around again, it would get down the curved path, throw the switch back to straight, and so on. This would be as like a very simple automatic route selection wiring system you can make just using one train and not having to block any sections of the track. I have a wiring diagram for this in that Getting Started booklet to do that. But you can see it just takes about 6 wires as I had wired up here earlier. Tape counter says I've only got 2 minutes on this tape, so I've got to talk fast. Consider this circuit using a 1201 switch motor and a 1203 relay points. We can take a simple switch and make an on-off siding. Consider the input comes in from a 1015U on this orange wire to the center of one of these sets of three terminals on the 1203, and the output is off the lower terminal as shown by the red wire here going back to this branch. This is a dead-end branch we're going to park an engine. I know from experience that when you push the arm over that way, which is what it takes to push a switch to curved, it connects the bottom to. If the arm was coming back the other way, like the switch was curved, that we connect to the top one, which we have nothing going to. But the way we got it wired, when the switch is curved and the arm is over, as shown by the arrow, these two terminals will be connected together, and that siding will get power. Let's take a look at that real quick. Circuit, you can see the same 2 wires. One input coming off this rail, which gets power from the main line, coming into the center terminal, going out the side terminal to the back part here. Power's on, so when I turn this to curved, notice that engine gets power. When it goes to straight, no power. When it goes to curved, it gets power. Straight, no power. So what happens when this switch is set to curved? These 2 terminals here get connected when you like that. When you set it to straight, it connects the input terminal, which is a center terminal, the red one here, over to that other one, which in this case goes nowhere and does nothing, but that siding is dead. So this is a simple way to make a siding that'll cut on and off. If you turn the switch toward the engine, it'll get power. If you turn it against the engine, it gets no power. This is basically how the automatic blocks operate on my automatic switching system. When the switch is turned toward the engine, it gets power and it can pull out of the automatic passing siding or the switch, however it's configured. If the switch is against the engine, it doesn't get any power and it can't go anywhere. Normally I would take this unused terminal and wire it over to this side so that the train on that leg would have power. That's how my automatic routing systems work and automatic switching systems.